নির্মল একটু চা করে দেন। তো আমি এই 15-20-তে করলেই হবে।
স্যার আমার কাছে আপনি ট্রান্সফার হয়ে গেছে।
So please click on the presentation and try to share your screen as a presentation.
So, should I start?
Sir, I will introduce first and then we can go with the presentation and demonstration. Just you can click on the presentation and try to share the screen. Yes, in the full screen mode. Yes, this one. Yes, okay. So very good afternoon, everyone. Thank you all for joining us today. I sincerely appreciate your participation in the 10th session of the Faculty Interaction webinar series titled Exploring Multifunctional Application of Novel Carbon Network Through First Principle Calculation with the Synopsys QuantumATK. So it is my pleasure to introduce our esteemed speaker for today's session, Dr. Utpal Sarkar. So Dr. Sarkar is currently an associate professor in the Department of Physics at Assam University, Silchar. He has made remarkable contribution to areas such as electronic structure calculation, nanostructure simulation, and designing of the novel material. His research is deeply rooted in advanced computational methods that continue to push the boundary of material science. With a strong foundation in the theoretical and computational physics, Dr. Sarkar has extensively explored the electronics, magnetic, thermal, mechanical, even transport property of the devices. In today's session, he will share the research insights on how Synopsys QuantumATK enable the first principal simulation of a novel carbon network at the atomic scale. His presentation will highlight how atomistic modeling and simulation are accelerating innovation in this involving domain. Following the talk, we will have a live demonstration by Mr. Nirmal Barman and Ms. Sadhana Barman, a PhD scholar under the Dr. Utpal Sarkar's supervision. So they will provide a hands-on walkthrough of Synopsys QuantumATK, showcasing its practical application in studying novel carbon network at the atomic scale. So with this brief introduction, I am delighted to hand over the session to our esteemed speaker, Dr. Utpal Sarkar. Over to you, sir.
Thank you, Deepakji, for your nice introduction about me and the kind words. Now we are coming to the point. Today's discussion is all about exploring multifunctional applications of novel carbon networks through first principle calculations with Synopsys QuantumATK. So we have used QuantumATK software extensively for last 5 to 7 years, and we have published quite a lot of paper. And not all about these transport calculations, some other like sensing.
Sir, sorry for the disturbing. Sir, just you can click on the cross sign on the screen of the right panel.
Pardon?
Click on the cross sign. Sir, click on the cross sign. Yeah, cross sign, cross one. Yes, now it's fine, sir.
Okay. So first, I will go for a quick overview of Synopsys QuantumATK overview, then atomistic model in QuantumATK softwares available, followed by the introduction of DFT and carbon allotropes, Then we will come to the main point, graphene as a ultra high capacity anode material for potassium ion battery, and finally the pentagraphene, whose thermoelectric coefficient will be investigated in this talk. Okay. So QuantumATK software is basically a complete software in my opinion, and in this software the main functionality is divided into two parts. One is the calculation level and another part is the GUI. GUI is very strong point of the ATK. Whatever you want to design for that is very easy to design using this GUI. And the calculation part is basically software's code. So I don't want to comment on that. Is optimization technique is really very good. What I found. And different types of calculations you can do, starting from molecular level calculations to polymer to 1D, 2D, 3D, that is solid state type calculations, amorphous calculations, and then device level calculations also. Okay, and GUI, this nanolab GUI helps to build the input features, input file for all these things, and help to analyze the results and help to create the pictures suitable for publications. And its DFT engine is really amazing, and it's really fast. What I have found, there are few softwares which are also available in the market, but this software is what I found is really very good. So it has input, and then once the input is ready, you have to put it in the simulation, and then once the result is you get the results, you can analyze with the help of GUI again. And there are two types of calculations you can do. One is quantum mechanical calculations and Newtonian mechanics, that is classical force field calculations. And classical force field calculations is mainly we also used QuantumATK for doing the molecular dynamics simulations using classical force field available in the QuantumATK, apart from the electronic structure calculations of the device and the battery materials. In between, there is semi-empirical method, tight bending methods that are also available here, and nowadays this machine learning force field also available. Machine learning techniques, these particular features is also available in QuantumATK nowadays. Now, anyway, what we have presented today is the work from the density functional theory. So density functional theory has two main theorems. You can consider it as a pillar of the density functional theory. The first theorem is Weinberg-Kohn first theorem, tells you that there exists an external potential, and the external potential and the electron density, there is a one-to-one correspondence between these two. That means that once you know the external potential of the system, then electron density can easily be derived from it, and otherwise if you know the density of the electron density of the system, then external potential can be derived from it. So characterizing one implies that you have already characterized the other one. However, this particular theorem does not tell you how to calculate the electron density. It is the second theorem, that is the variational principle, that tells you how to calculate the true ground state electron density or the energy. So the trial ground state energy, suppose it is ET, satisfies the relations E0. E0 is the ground state energy, that is basically less or equal to trial density ET. Suppose you are starting with some trial density which is not the true electron density of the ground state of the system, then whatever the energy you will get, that actually is higher than that of the ground state. The ground state energy you will get if and only if you start with a true electron density of the ground state, then only you will get the total the ground state energy, and after you get the ground state energy, you can calculate with the help of this electron density all the density related, electron density related property. And what we have shown here is that the key parameter here is the electron density. We have calculated the electron density, and then from the electron density itself you can calculate, and that is the beauty of the density functional theory. So once you know the electron density of the ground state, then you can characterize, you can calculate all the response functions and the energy related things from the electron density itself. So how do you calculate the electron density? So perform a constant variation of these particular expression, energy expressions. So this is your energy and this is your electron density. So if you integrate the electron density over the whole volume, then it should be equal to your total number of electrons, that is this quantity. And so this quantity, if you just take a variation of it, these variations will tells you the how to calculate the Lagrangian determinant multiplier of this equation. So Lagrangian determinant multiplier is basically from this expression is del del rho of E rho. And but now in 1984 Professor Parr first identified that this Lagrangian determinant multiplier is nothing but the chemical potential of the system. So this is the first identification of chemical potential from the electron density, and once you get the chemical potential of the system, then the whole of the chemistry can be explored from these particular expressions. So now all chemistry people jumped into this field, and then a huge bump in the publications in density functional theory, basically from the organic chemistry community. And as a result of this very good success of the density functional theory, in 1998 Nobel Prize in Chemistry was awarded to Professor Walter Kohn for his development of the density functional theory, and Professor John Poppel for his development of the basis set, Gaussian basis set available for the density functional theory. And Walter Kohn and Poppel both are not from the chemistry background. Walter Kohn is a solid state physicist and John Poppel is basically a mathematician, and both of them got Nobel Prize in chemistry. So it's basically a mixture of physics, chemistry and mathematics, so interdisciplinary things we'll discuss now. Now let's have a look on the carbon allotropes. So here graphene is situated, and then once you functionalized it by hydrogen, you will get graphene, oxyfluorinations, and OH functionalizations, you will get graphite oxides. So all these systems are basically sp3 hybridized systems. Now from graphene you can also get sp2 hybridized systems, like when you are rolling this graphene, you will get single wall carbon nanotube, multi wall carbon nanotube, and if you stack one after another, and then you will get graphite. Similarly, if you include pentagon and then roll it, you will get graphene and fluorine and multifluorine, and these systems are basically sp2 hybridized systems. If you include acetylene linkage between the carbon-carbon between the carbon-carbon bonds. You will get graphene, graphene 3 and graphene 4. These are sp2 hybridized systems. Similarly, if you introduce topological defects, then you can get pentagraphene, and inserting acetylene linkage, you will get pentagraphene, T-graphene, SDE graphene. These are basically examples of sp2, sp3 hybridized systems, sp2, sp3 hybridized systems, this one. So you are getting a lot of combinations of different hybridizations using carbon electrodes. We will explore this one by one. Now, for a specific example, we will see whether this naphine, this is a unit cell of a naphine. You see, this is fused benzene ring, and then this is basically the if you consider this one, this is basically part of a graphene family, and then they are joined together, and it's basically a unit cell of naphine. And this is the supercell, 1x2x1 supercell of naphine. And now this particular structure, you see, this has ports, smaller ports, a little bit larger ports, and triangular ports like this. So different types of ports are available in this structure that is suitable actually for absorbing the potassium ions in this port area. And due to the porosity, varying porosity, it is helpful for sodium, so that after absorption of sodium, its distortion is basically less. And due to the presence of acetylene linkage here, this structure shows some peculiar characteristics for ion diffusions. Okay, so when we have absorbed sodium, its absorption energy, these are the particular sites of sodium absorptions we have tried. So out of these 5 absorption sites, these 3 are basically the central pore region of these particular pores. So out of, and these are the 2 bonds we have tried on the middle of this. This is basically a transition state. Okay, so here also a local minima is available here and here, so we have also tried that one. And now we have considered the energies of all these 5s and found that this A position, this triangular hollow positions, middle of the triangular hollow positions is best for sodium absorptions, and its absorption energy is roughly minus 1.967 electron volt. And this sodium is basically situated at 2.25 angstrom above the plane of this seat. And this seat, we have performed 𝐬𝐽 calculations, as well as we have considered the van der Waals interactions, and we have seen that the van der Waals dispersion energy associated with this is basically minus 0.227 electron volt. Now look at whether this structure is okay, no problem, but whether this structure is stable one or not. For that we have first check the dynamical stability. This is the phonon band structure. The phonon band structure clearly shows that there is no negative frequency available for this. That means this structure is dynamically stable, and if you give a small perturbation to this system, the system will be retained in its initial returns its initial geometry without any distortions. And then we have seen the thermal stability, because battery will operate at least at some room temperature. So this is a pristine system, and this is the lithium sodium absorbed system. This is temperature versus time plot. So up to 5 picosecond. We have seen how the temperature varies for this naphthalene system. You see, it's basically temperature is basically fluctuating around 300 degree Kelvin, and here in absorb system, potassium sodium absorb system, you see it's there is no that much fluctuations. Once this initial transients is over, then it's basically fluctuating around very small values. Similarly, the energy. Similarly, the energy, this potential energy graph also tells you that there is not that much fluctuations in the potential energy curve for pristine system as well as potassium sodium absorbed system. So that means these systems are thermally stable. Okay, so the thermal fluctuations are basically very less. You see, even after the absorption of 48 potassium ion on this naphthalene sheet. So no structural distortion, a very small amount of structural distortions we have found. That means the systems are thermally stable. Then we have calculated the cohesive energy and formation energy. Cohesive energy per atom. So for a pristine system, is cohesive energy is minus 8.225 electron volt per atom. That means this is a very large number. It implies that the system is basically very stable one. And after absorbing potassium ion, its cohesive energy is decreasing, but still negative. Okay, and then that means the systems are basically stable even after absorption of 48 number of potassium ions. Now you see that formation energy is basically initially it is 0.69 and then it is decreasing trend. So more and more potassium ion, when it is increasing, is yes. So is basically its formation energy is basically decreasing. That means is favorable. The process is basically favorable. That means from this we can conclude that the pristine naphthalene exhibits high cohesive energy. That means here this value, that means the carbon-carbon networks, the carbon-carbon bonds are very strong bonds, and that reflects the structural stability or structural integrability of the system, and that pertains even after the absorption of sodium atoms, 48 sodium atoms, potassium atoms. Sorry. Now, this is the structural deformations. So this is A and B. It is a two-dimensional system. So in the C directions, it is one atom thick. So we have not considered this C, A and B. So single potassium ion. What is how these lattice parameter A and B changes and lattice expansion in terms of percentage we have given here. You see that. After absorbing potassium ions, the change in lattice are not that much. It's only 0.65%, 0.65%. So percentage change is very small. That means is structural deformation is negligible, and for other two-dimensional materials, whatever available in the literature, if you have a look on that, the structural changes is basically 4 or 6.07%. So it's much more higher. The structural deformation is much larger for other materials, whereas for naphthalene, the structural deformation is very less. You can see here. So this system is very stable for absorbing potassium ions. Now, after absorbing potassium, what is the band structure of the system? Initially, this is the band structure of napine. You see there is a clear band gap here available. So the band gap is 0.272 electron volt located at this X point. However, after absorbing one potassium ions here, this is the band structure, and you see these two bands are now crossing the Fermi level. So these systems are now metallic. So why this is occurring? So here this band gap is occurring because there is no available states near the Fermi levels, and near the Fermi level only the pz orbitals are available, and the contributions of other orbitals are very large away from the Fermi levels. But here you see, after absorbing one potassium ion, the pz orbitals of carbon atoms, you see here the pz orbital of carbon atoms are basically contributing in the Fermi level, and that's why these crossing of these two bands are occurring. So these two bands are basically originated from the pz orbital of the carbon atoms. However, a ps orbital of carbon is located a very large area in the conduction band. Is around 2.5 electron volt, you see here, and others are basically located around minus 1.5 and so on and so forth. So basically the pz orbitals are basically contributing for this band structure, and that increases the electrical conductivity after the absorptions of potassium ion. So the system is now metallic and suitable for conductions, and now we can use it as a battery. So preliminary verification is over. Now after absorbing the potassium ion, how our bonding nature changes of the piston system as well as in the absorbed system. So this is a electron localization plot that you can do using QuantumATK softwares. We have done it through QuantumATK softwares. Now you see from this piston system, these are basically the electrons are localized around these carbon-carbon atoms. You see here these carbon-carbon atoms, electrons are basically localized, and electrons there is here in this region the electron localization is 0 or basically delocalized. So this particular structure tells you that this is basically a covalent in nature. However, you see here and you see here, this covalency is basically this covalency is now decreasing, and non-covalent type interactions, ionic interactions is basically coming when you are putting the potassium ion on the top of this structure, and you see here in this particular region here and here, you see this is basically a spherically shaped, and this is, you see, now it changes its structure, so it's basically ionic in nature. So ionicity is now coming here, which is was clearly absent in case of covalent bonding here. So non-covalent bonds are now coming when you are putting the potassium ion in this. So potassium ion absorption tells you that there exist non-covalent interactions between potassium and carbon atoms, whereas carbon-carbon interaction is basically totally covalent in nature. So covalent means different types of bonding you can get from this software, and we have demonstrated only one of this because of the time constant. By half an hour I have to finish, so I'm sorry for that, but actually I will try to cover as much as possible. The next part is the diffusion, and that tells you how these absorbed potassium ion migrates from one particular atomic site to the other position, other minimum. So from here to here or here to here, it from one stable position to another stable position, there are 3 paths available here. This is one, and another one is on the top of this ring, and another one is that on the top of this ring. Okay, so here if you see here, there is only one barrier here, or that is this one, and we get this energy barrier is about 0.37 electron volt, and but here there is a local minima here, so that is perfectly reflected here. So energy barrier is now a little bit larger, it is 0.39 electron volt, and but from here to here you see the energy barrier is the energy barrier here is a little bit larger, you see 0.52 electron volt. So basically from here this potassium ion tries to migrate along this path. However, these paths are also available depending upon the energy available for that potassium ions. So diffusion barrier is a little bit lower in this path, and most of the migrations are occurring through this path. So this low diffusion barrier tells you that this diffusion coefficient is basically large. Next, we have calculated the open circuit voltage. Open circuit voltage for different number of potassium ion concentrations, and overall we get the open circuit voltage as 0.37 volt. Now, this tells you that for optimal anode material, the voltage window should be 0.1 to 1 volt, and now we get an average open circuit voltage of 0.37 for this particular material. That means tells you that this is basically this material is suitable for electrochemical performance, and it ensures the thermodynamic compatibility with high voltage cathodes. Theoretical storage capacity for all these layers we have calculated, and we get the theoretical capacity of 1487, means roughly 1500 milliampere per gram, is basically very large. And finally we have shown that the absorption energy with how this absorption energy changes with the number of potassium ion. We see that the absorption energy is negative from first layer, second layer, third layer, fourth layer, fifth layer, sixth layer, and then when you are trying to add one next layer, then your absorption energy becomes positive. That means it cannot accommodate more than 6 layers. Okay, so it can accommodate up to 6 layers of potassium. So this is this layers up to this one. Okay, now this is a comparison of theoretical storage capacity, open circuit voltage, and diffusion barrier for this naphthalene material. Naphthalene we have this storage capacity of roughly 1500, and other reported materials are basically less than this. You see here open circuit voltage is moderate, you see from here, and this absorption, this diffusion energy barrier, you see here is basically roughly, you see other materials it is 0.48, 0.9, 0.7, some are basically very less definitely, but ours is in between. So combining all these 3 parameters, you can say that naphthalene is basically a suitable material for potassium ion battery. So our conclusion from this study is that naphthalene is identified as highly promising anode material for potassium ion batteries, offering a viable route for next generation energy storage. It delivers an ultra high theoretical capacity of 1487 milliampere per gram, significantly surpassing the conventional carbon based anodes, with stable absorption up to 48 ions per K48C72 unit, means one particular unit, and excellent potassium ion transfer properties, including low diffusion barrier and high diffusion coefficient, enables fast charging and high rate performance. Structural integrity is another important thing here, is maintained during the potentiation and exhibit minimal lattice expansion and strong mechanical robustness and resistance to volumetric stress, ensuring long-term cyclic stability of this system. Potassium absorption includes semiconductor to metal transitions and markedly improving electronic conductivity and facilitating the electronic efficient charge transfer. A favorable open circuit voltage of 0.37 balances high energy density and operational safety and reduce risks such as dendrite formations. And overall, the synergistic combinations of ultra high capacity, fast ion kinetics, structural resilience, and electrochemical adaptability positions Nafine as a next generation and for high performance, cost effective, and eco-friendly potassium ion battery systems. The second example we'll consider is the pentagraphine, and we'll see whether it can be used as a thermoelectric material or not. Okay, so materials that can convert heat into electricity or vice versa, that are basically called the thermoelectric material. And in physics there are two types of effect known for it. One is Seebeck effect, which transforms heat into electricity. Another one is the Peltier effect, just opposite to it. So it transforms electricity into heat. Okay, so this is our proposed system, pentagraphine. For that, we'll try to understand the thermal properties. This unit we have generated from the pentagraphine system proposed by Professor Jena et al. We have inserted an acetyl linkage in between these two, and that makes a huge change in the thermoelectric properties of the system, what we have identified. So acetyl linkage increases here the lattice parameter from 3.64 Armstrong to 9.85 Armstrong from here to here. And structural thickness, this system is a buckled system. Its thickness is basically 1.22 Armstrong, whereas if you insert the acetyl linkage in between this carbon-carbon, then its thickness becomes 3.4 Armstrong. The geometry becomes more open here. You see the porosity is increasing and more buckled compared to pristine pentagraphine. And hybridizations here is basically sp2 and sp3, but here it is sp2 sp3 network it is forming. So these structural these hybridizations that makes a distinct difference in the electronic properties and also in the thermal properties. Now, how do you identify a material to be a good thermoelectric material? For that, we have to calculate basically ZT, which is basically calculated through this formula. The S is the Seebeck coefficient, T is the temperature. This is the electronic part of thermal conductivity and phononic part of thermal conductivity. Okay, so now to increase the ZT, you have to increase either G or S, or you have to decrease this K, E or KPH. KPH value is very, very less compared to K electronic part. Electronic part is basically more dominating than the phononic part. However, phononic part also gives some contributions. So now for which type of material we will propose here, we need Seebeck coefficient higher. Okay, so if you consider a metallic system, then Seebeck coefficient will be less. So narrow bandgap semiconductor, if you increase, means 2 narrow bandgap means Seebeck coefficient will be less, and it is not very suitable. Too large if you give, then your electrical conductivity will be very less. So this quantity will be again then less. So it's basically a problematic thing. One increasing, if you try to increase one, then you have to decrease another one. So that you have to play with in which particular value it gives the maximum safety. Now high DOS, the thing here is that from this you have to identify a system whose band gap is moderate. That means is high DOS with asymmetry around the Fermi level. Then you will get a enhanced Seebeck coefficient. Seebeck coefficient is a square quantity that will tell you much more effect in ZT compared to GE. কতক্ষণ টাইম আছে? So for a moderate, this is the expression for area mobility of the system, and to moderate effective mass ensures if you have a system whose effective mass is moderate, then that ensures that it is S and G is basically good for this thermoelectric material. So too high mass, effective mass, then that means is poor mobility, and Seebeck coefficient, if it is very low, then is Seebeck coefficient will be low. So our higher ZT means better thermoelectric performance, and better thermoelectric performance means I have to get ZT whose value is greater than 1 for practical applications. And now we have designed, using this concept we have designed, and why we have designed, because it directly converts heat energy to electrical energy, and using this one you can control the temperature, you can use waste heat, you can efficiently energy for the device is energy efficiency will be increased. So for this particular reasons, this thermoelectric device is important. Now this is the main part of the calculations. I have to make a device, thermoelectric device. This is the unit cell of it, and we have to repeat. And the systems along the Z directions, let's say here in the X directions. This is the left electrode, this is right electrode, and in between this is central region. This central region comprises of three regions. One is the scattering region. This is the main scattering region, and this is basically extended left electrode. This is the extended right electrode. So central region comprises of scattering region plus extended part of the left electrode, extended part of the right electrode, and the length is given here for each of these. We have first part, we need electronic part, we need phonemic part, both for the thermoelectric calculations. So we have first try to understand the band structure of the system. So this is the band structure of pristine system. A band gap turns out to be 0.98 using PBE method, and using HSC functional it is 1.71 electron volt, and it's basically a jet band gap semiconductor you see here. And this is the projected density of states of the system. Here you see the main contribution is coming from the EZ orbital of the carbon atoms, and there is no states available near the Fermi level. So this band gap is completely explained with the help of this DOS. This is the DOS of the device, partial density of states of the device, and here you see again this is the contribution of the carbon p orbitals That is basically mainly contributing in the loss of the device also. Now, transmission spectra. This is the transmission spectra for the electronic contributions. This is the phononic part. Okay, so phonon band structure, transmission spectra from the phonon, transmission spectra from the electron. You see, this is basically in the conduction band. There is a contribution here, and it's almost symmetric here. However, this part is basically due to the phonon. The phonon transmission spectra, you see, the peak is available for very small energy range, and after here actually we will see the phonon band structure. Yes, you see here, this is the phonon band structure. And this is basically the acoustic modes, 3 acoustic modes. The highest acoustic modes frequency is almost 7.33 millielectron volt. Okay, that we will try to find out in our transmission spectra. And this is the phonon band structure of peacetime, but pentagraphene. This is penta. You see these hello.
Yes, sir, you are audible.
Okay. So when we are inserting the acetylene linkage in pentagraphene, you see that the bands, these optical bands here, these are basically zigzag in nature here. Curvature is goes out and it now becomes flat. That means this 𝐬𝐭𝐫𝐿, this group velocity in the after inserting the acetylene linkage for this pentagraphene system, the group velocity is basically 0. That means this phonon phonon bands are mainly localized, and they are not moving in the within the material. So this phonon modes are not contributing to the thermal transport. Whereas here you see there is this is an acoustic mode. This phonon mode. So here this group velocity is not flat, and the group there exists some group velocity for these phonons even in the low energy region. This is a high energy region. Even in the low energy region, they contribute to the thermal transport because it has a non-zero group velocity, and the phonons amounts are not basically confined in that particular positions. But here you see here you see this is the transmission spectra for the pentagraphene system. You see highest transmission is observed for very small energy range. That means all these energies are basically contributing for here, and highest transmission is observed around highest transmission is 5.5, and that occurs around this 0.2 or something, 0.02 electron volt, something like that. And in the high energy region, you see here only few modes are available, and its intensity is also decreasing. Its intensity, that means this transmission for phonon contribution here is basically for high energy phonons are basically decreasing. High energy phonons contribution is basically decreasing in case of pentagraphene. We have considered the Seebeck coefficient, calculated the Seebeck coefficient. The highest Seebeck coefficients is here and here for this 200 degree Kelvin, 300 degree, 500 and 700 degree is situated here. You see that once you are increasing the temperature, when we are increasing, our Seebeck coefficient is basically decreasing. So the Seebeck coefficient measures the magnitude of the voltage produced per unit. This is the definition, and superior. These our Seebeck coefficients are basically superior than the known material like B and SIT and other two-dimensional boron phosphide 6, dapdine, etc., etc. So in terms of only Seebeck coefficient, this naphine is better than the already reported values. This is the electrical part of the electrical conductivity. You see at different temperatures we have calculated. So electrical conductivity is basically you see here it is higher for 200 degree Kelvin, and then 300, 500, 700 it is basically decreasing in order. So increasing temperature and yes, the conductivity is electrical conductance is basically decreasing. That means the higher electrical conductivity is basically reduces its Joule heating. So this is a very good material. Thermal conductance. This is the electronic part of the thermal conductance. It's for different temperatures. Here you see for different temperature regions. You are getting electrical conductivity with increasing temperature. Your electrical conductivity increases, and this is the phononic part. This is also increasing. So total conductivity is basically increasing. So low thermal conductivity prevents thermal shortening. And from this graph you see that here this is pentagraphene case. When you are increasing the temperature, your phononic part, acoustic part and optical part we are giving. Here the acoustic mode contribution is decreasing, however optical part is increasing here for pentagraphene. Same is occurring here also. The trend is same, okay, but here you see the acoustic mode is contributing less in case of pentagraphene, whereas optical part is contributing most, because here optical you see these are basically contributing more here, and calculated value are this much. However, when you are inserting acetylene linkage in here pentagraphene, you see your optical part, these are basically plane, these are basically straight lines now. So its curvature is 0. Now its contribution is decreasing with respect to the previous one. With respect to the previous one, the optical part is contributing less. However, the acoustic part is contributing more in case of pentagraphene. Okay. So, so we conclude that this particular material is good for thermoelectric performance. It gives higher ZT, and this ZT we have characterized using Seebeck coefficient, using electronic part of thermal conductivity, phononic part of thermal conductivity, and in terms of HG. Okay, so my conclusion is highly sensitive to chemical potential. This Seebeck coefficient or all these things are highly sensitive to chemical potential and temperature, and ultra high Seebeck coefficient we have achieved. Electronic contribution dominates over phonon contribution. It should be, and pentagraphene sustains this much. You see, ZT is roughly 1.15 to 1.26 within this temperature. It is greater than 1 within this 500 degree Kelvin temperature variations, indicating strong potential for efficient energy conversion across a varied temperatures. And optical phonon dominates, that is thermal transport in pentagraphene 80% at 200 degree Kelvin and rising to 89% at 700 degree Kelvin, while the acoustic mode contribution drops 20% to 11%. And pentagraphene's unusual phonon transport leads to low thermal conductance, boosting thermoelectric efficiency and making it a promising next generation material for sustainable energy solutions. And this is the machines we have used. QuantumATK is installed here. Apart from QuantumATK, we have also used CS, the Quantum Espresso, fast Gaussian. And this is my small PhD team. So this is Harkishan, Nirmal. We are present in Nirmal's work here. They are working in our lab, and my past PhD students. Everybody has contributed in some way or other. I would like to thank my collaborator, Professor Bodhin Chatraj from IIT Kharagpur, Professor Paul Ayers from McMaster University, Canada, Nicholas Siriani from ICTP, and Bhomananda Chakraborty from BART, Mumbai, Sandeep Sharma from Amritsar, and Hafez Sadeghi from University Warwick, UK. And the funding agency DST SARB and DBT NCDH for giving us funding for this work. Thank you. So can we go for the second part of our talk? Thank you. Thank you to Dr. Chakraborty. Thank you so much. শুনতে পাচ্ছি কি শুনতে পাচ্ছি or is there any message here? Hello.
Yes, sir. So thank you, sir, for this nice presentation. Now I would like to invite Mr. Nirmal Barman for the demonstration of this Synopsys QuantumATK.
Yeah. Nirmal, please.
Hello. Actually, the first part of the hands-on section will be demonstrated by Sadhana Barman. Then I will.
Okay, no, sir. Okay, no, sir. Okay. Yeah.
Good afternoon, everyone. My name is Sadhana Barman, a PhD research scholar. So, my part of demonstration will be covered the energy convergence criteria and optimization of unit cell to device, and I will cover two-part based on the two reported geometry that has been discussed by sir. One is the naphine and another one is the pentagraphine. So first of all, I would like to start from the unit cell energy convergence criteria, and I will demonstrate all the part step by step. So here I am opening the unit cell of the naphine. In the QuantumATK software, here is the unit cell. You can see that has been reported in the JPCC paper. So this is the unit cell of naphine. Now we have to, before doing the property simulations, we need to have a very stable geometry, optimized geometry. So for this, we need to check the energy convergence criteria by two ways. One is the E-cut and another one is the K-point sampling. So before going to the energy convergence, you need to monitor the structure visually, whether the structure is okay or not, because sometimes what happens is that due to the overlap of the atoms, the geometry is not visualized properly. That's why now going to the script generator. Here you can select the 𝐬𝐻𝐿CO calculator here. The exchange correlation will be given here. You can choose according to your convenience. Here I have chosen the 𝐬𝐺A. Another one is the pseudo potential, pseudo dozo, and basis set I have taken as medium. Here now we are going for the density mass cutoff convergence. So you have to gradually increase the value of the density mass cutoff. So first of all, you can see here, this is the 55, which is the default value. You need to increase the value in the step of 5, or you can take it up to, it will be up to on you. By 10 also, you can also increase it by 10, 60 to 70, then 80, then 80. I am taking here the 80. Now go to the, after setting the 𝐬𝐻𝐿CO calculator, you go to the analysis part. Here you will see the total energy black here. Now you have to click the total energy and save the structure as it is. In one file you can save it. I have saved it like E, and it will save it as a py file. You can see the structure, whether it is saved properly or not. See here, here the py file has been saved properly. Right click. Open with right click. Open with
That's one.
Here this is the e.py. You can see this is the py file that has been saved for the energy convergence criteria. Now now you can go for the simulation. Now you can go for the simulations, and you can monitor the total energy in the log file. I am showing you the log file also, how it will be printed, the total energy. I have taken a already simulated geometry for your convenience. This is the yes, you can see this is the log file. In the last part, sorry. Sorry, actually I can show you the log file for the PNL also. So you can see here, if you click in the HDF file, you can see a flag. Here you will see the total energy, and you go to the text representation, you will see the total energy. You have to monitor this total energy, and you have to take care of the. We are just looking for the saturation up to the 3rd decimal point. So that the change in the total energy should be negligible. Then we can consider it as a consider density mass cutoff. Then we can take that density mass cutoff for the optimization. Now, we will go for the, once the density mass cutoff has been set properly, now we will go for the K-point sampling. Here you have to choose the sampling, and you can choose in by step of 1 or 2. Like here it has already set 2 for 1. you can set 2 and this is 5, or as the z direction is frequent, that's why it will be set as 1. Likewise, you can also save this as pi file. Here it will be same as the density mass cutoff, so I am not going to save it. So so as you can see, for the k-point sampling also you can see the total energy. So for k-point sampling also you have to monitor the total energy, and you have to take care of the saturation up to 3rd decimal point, so that the change in energy will be negligible. Then we can take that k-point sampling for the optimization. Now I am going for the optimization part. Once we get the density mass cutoff point and k-point sampling, now again we have to go to the script generator, set the alcohol calculator. You can set the exchange correlation pseudo potential according to your convenience, and choose the k-point that you got from the energy cutoff convergence criteria and the k-point sampling. Here I am putting the default only because I have to show the optimization part now. This is the optimized geometry you have to choose, and here you have to choose the force tolerance and stress error tolerance. You can set a different threshold values, whatever you need. So I am putting here the default values, and the one important part is you have to unfix the lattice vectors for doing the optimization. So here I am unfixing it, the previous lattice types. This part also you have to unfix it, and now this is the file name. You can go for save to save the structure, and also you can monitor the total energy of the optimized geometry. That's why I am setting the total energy part. Again, you can save it. This you can save it as I have saved for the energy convergence criteria. You can save it as pi file 2. So I will go again to the pi file. Now I will show you the the optimized geometry, how it will look. So this is the optimized geometry that I have already taken. Here you can see that the lattice parameters have been changed. You can see after the optimization, the important part is to see the lattice parameters which has been changed. Now we have successfully done how the convergence criteria can be done for the unit cell and optimization. Now I will proceed to the second geometry which has been reported in the ACS journal, the pentagraphine. See, so this is the pentagraphine structure. I have taken it from the optimized geometry. Now I will go for the device construction and optimization. So this is the unit cell I have taken. For device construction, you need to go for the repetition in the C direction. You have to repeat it in the lateral directions. I am repeating it in the C direction according to the paper that has been reported. So I am repeating it in 3 times. Here you can see the 3 times it has been repeated. And now you have to construct the device. So for constructing the device, you need to go to the device from bulk option. So if you go to the device from bulk structure, the device will be constructed. See, you can see here the device has been constructed. So in the device, you can see that this part is the central region, and this 3 unit cell, you can see this part is the central region. Also for more in detail, you can see the paper, and this is the left electrode, and this is the right electrode, and this is the main scattering region, and this is the extended version of the left electrode, and this is the extension of the right electrode. So this is the device we have constructed from the optimized geometry of the unit cell. So for the device optimization, again you have to go for the energy convergence criteria. which is same as the unit cell. Again, you have to go for the script generator. You have to set the 𝐬𝐽 calculator. Here you will again put the density mass cutoff and gradually increase and monitor the total energy from the log file, and again take care of the saturation up to 3/3 decimal point, and we have to check whether the energy has been, the change in energy has been negligible or not. At that point you have to take as density mass cutoff, and again you have to check the sampling. So this part is same as the unit cell. Now you have to go for the optimized geometry. Here also you can choose the force tolerance. You can take whatever you need. Here I am putting here the default value only, and again there are the optimizer method is also there. We have done in 𝐬𝐵𝐹-GS method, that's why I am putting 𝐬𝐵𝐹-GS method here. You can change it to fire also. The geometry file has been saved as device_core_trajectory. Now again you can also put the total energy also, like the unit cell. See here you can put the total energy, and again you can save the structure, and now the device is ready for the optimization. And after getting the optimized geometry, now you can simulate the transmission spectrum or the transport properties for thermoelectric device and for the other properties. The subsequent property simulation will be covered by the Mr. Nirmal Barman. So my part is over now. I am now hand over the session to Mr. Nirmal Barman. Thank you. Hello.
So should I start?
Yes, please.
Okay. Good afternoon, everyone. My name is Nirmal Barman. So up to the optimization step, I think everything is clear, which is demonstrated by my junior Sadhana Barman. So now here I will demonstrate the various properties for various application. Basically here I will show the two application. One is battery and another is thermoelectric materials. So we will start with our battery work, which I have published in JPCC. So basically I will show the result and discussion section. So for the analysis section, we have to first optimize the structure. So suppose the structure is optimized. Basically, suppose this is the unit cell. Suppose this is so we have to make the input for optimize. So for suppose the structure is optimized, so we have to calculate the various properties. So for calculating the various properties, the first step is to select the structure and first select the structure, then we have to go in the calculator. So we will choose 𝐬𝐽 calculator. 𝐬𝐽 means linear combination of atomic orbitals. Now we will choose the converse parameter. Suppose our converse density mass cutoff is suppose 100, and the K point is suppose 10, 10, 1. Since it is 2D, so the K point should be x, y, 1. When it's along the z direction, it should be 1. So this is the suppose converse K point, and 100 Hz is the converse density mass cutoffs. Then we will choose the 𝐬𝐽 basis. Suppose if we choose van der Waals DFT D2 or DFT D3, or if we calculate only GG and PB level, then we should put it disable. Suppose we will calculate, since in our JPCC paper we will calculate in DFT D2 van der Waals correction. So calculator part is completed. Then we choose analysis. Since the structure is already optimized, so we will not go in optimized section. We will go direct analysis section. So for analysis, so first we will calculate electronic properties. So here actually for electronic properties means band structure. So we select band structure, and then we will calculate projected density of states. Projected density of states. In projected density of states, we will also get total dose. So since our structure is carbon based material, so we will choose element orbitals, and the structural spectrum method is tetrahedron, and sampling is if the converse K point is 10 10 1, so we will choose double of converse K point, so 20 21. Then it is, and the energy range I will choose -3 to +3 electron volt. And band structure here Y is G X these are all the high symmetry points. So suppose for Nafan system, the high symmetry point most probably gamma X RY gamma X RY gamma. So this for all the high symmetry points, and this is projected density of states. Then we save it as Nafan electronic. So our input is ready for electronic properties. Next we will calculate after the suppose if our electronic structure, the input for electronic structure calculation is ready, then we will calculate the other properties like suppose NEB calculation, NEB, or suppose open circuit voltage. Actually open circuit voltage adsorption maximum theoretical capacity all are from adsorption type properties. So we have to okay. So for adsorption properties, we have to increase the unit cell into 1 cross 2 cross 1. Actually, we have published in JPCC in generally for battery anode materials, we will adsorb the potassium or any type of ions in the on the supercell. So we have to first repeat the unit cell from unit cell into supercells. So for supercell calculation, we have to select in the right parts of the VNL section. One is repeat options, and under the repeat option we will see A, B, and C. So for our calculation, we will repeat along B direction, 1 cross 2 cross 1 supercell. So suppose the supercell is ready, then we will put we will add the potassium ions on the Nafan supercell. So since this side is the most stable side, so we now we will adsorb potassium ions on the most stable adsorption side. Suppose this is one structure, and we will translate the potassium ions along the C direction at 2.59 distance. Above the plane. So for this, you have to select the potassium ions. Okay, the input is ready for single potassium ions. Accordingly, we have to put one by one on the 8 for adsorption sites. So after absorbing the 8 ions, we will get the first layer. Accordingly, opposite of the first layer, we will get the second layer, and similarly, we will get the maximum 6 layers. Then we will go for NEB calculations. So NAP calculation, actually we will do NAP calculation for calculating diffusion energy barrier and also the diffusion coefficient value. So for NEB calculation, we will show for only actually in the JPCC paper we have shown actually 2 paths. So here I will show only one path. This to this actually. So we have to make the input for second positions. So we will duplicate it. Suppose this is the first position and this is the suppose second position. So for NEB we have to go in builder section. Under the builder section there is one option in non-elastic bands. So we have to put these options, and here two option we have seen actually initial and final. So in the initial part we have to track the first site or first positions, and in the final section we have to put the second positions. Now we have to choose image dependent pair potential, and now we have to create for NEB inputs. If we now our NEB input is ready for NAP calculation. So this is for the path 1. Similarly, we have to calculate the other parts on the anode materials. So NEB is so now we have to make the input for NEB calculation. Then we have for making NEB calculation we have to go in script generator section. Now choose 𝐬𝐿 calculator, then optimization. In optimization section we have to go select climb image methods and optimize points. Actually in NEB calculation and another parameter is force tolerance, and we have to choose the force tolerance 0.01 electron per angstrom. And now we will save the input for first NEB calculation. So NEB input is ready. So after running this NEB calculation, so after running the NEB calculation, we get the output like suppose NEB. Then select the HDF one. Actually, one is the optimized NEB file. Then select the one NEB1 HDF1. Then we will go in Movie tool. and here is the NEB path, NEB graph actually. And for our path 1 calculation, the diffusion barrier energy is 0.38 electron volt. And similarly, we have calculated the NEB for second path, which is and the energy barrier for path 1 is 0.38 electron volt. Actually, Y is the barrier actually. Y is equal to 0.38 electron volt. And here and the circle part point is actually the number of images that we have used for calculating NEB calculation. And for open circuit voltage and others properties like the maximum theoretical capacity, these are all basically these are all calculated from the formula, which is based on the now next I will demonstrate the thermoelectric properties, which is published in ACS Applied Energy Materials. So for thermoelectric properties, we have to first optimize the device. After optimizing the device, we will suppose if this is the optimized geometry of the device. Suppose this is the input file. So this is the device optimized geometry of the pentagraphene device. Here is the first one is the central scattering region. So now we will calculate the transmission spectrum, transmission properties like 𝐸𝐵𝐽 transmission properties, and under the transmission properties we will calculate all the thermoelectric properties like 𝐸𝐵𝐽 coefficients. So for this we have to again choose 𝐬𝐭𝐫𝐽 calculator. Then we have to choose analysis section. In analysis section there is an option transmission spectrum. Then we have to select transmission spectrum. This is actually electronic transmission. So here we have to choose the energy, then sampling. Actually for sampling we have to choose the convergence. Actually, suppose if the since it is we have calculated the transfer properties along a particular direction like x direction or y direction, so we are accordingly the sampling will be sent. So suppose if the sampling is 1 cross 5 cross 1, and we have to here we have to choose the energy range, and suppose the energy is minus 3 electron volt to plus 3 electron volt. Now the transmission properties, now the input for transmission is ready. So after simulating the transmission input, we will get the results like here. We will get that results like phonon transmission spectrum _1, which is the output of electronic transmissions. Then we will go in the transmission spectrum, transmission analyzer, which is right out of the VNL. Now we get the transmission spectrum graphs for electrons, and similarly we will calculate for the transmission for phonons also. which is time consuming calculation, and after the transmission we will get the we can calculate the thermoelectric coefficients like Seebeck coefficients. So for calculating Seebeck coefficients and other thermoelectric properties, we have to select the transition. Then in the right part of the VNL, there is an option in thermoelectric coefficients. Then we have to select the thermoelectric coefficients. Now we have to select the temperature. Suppose temperature 200 Kelvin. And since in the transmission during the making for transmission input, we have to select the energy range from -2 electron volt, -3 to +3. So here we have to put the energy range -3 to +3, and here we have to put the number of steps. That's suppose the number of steps, suppose 1000. Now it is the plot options. So VNL so it's a VNL problem and visualization problem. Okay. Electric coefficients and let's see. Point of view. Okay, sir. Okay. So this is a Seebeck coefficient plot. Now on the top of the left side, we will see actually different type of thermoelectric properties. One is Seebeck coefficient, conductance, Peltier coefficient, Seebeck coefficient, thermal conductance. Suppose for Seebeck coefficients, this is the graph for Seebeck coefficients. Suppose if you want to extract the data, then save options and save as. Extract data, then we can extract the Seebeck coefficients data as a .tx or DAT format. Similarly, we can also calculate the conductance. This is the conductance plot in the energy range -1 to + electron volt. Similarly, we can get the thermal conductance, and this is the ZT. This is the ZT for actually electronic thermoelectric coefficients. So these are all the thermoelectric properties due to electronic contribution, conductance, Seebeck coefficients, and electronic thermal conductance, and electronic thermoelectric figure of merit. Similarly, for other two properties for due to phonons, one is phonon thermal conductance and another is phonon thermoelectric figure of merit. So for phononic part, we have to make the input for transmission due to phonons. So for suppose this is the optimized geometry of the device, and for phonon transmission spectrum, we have to select script generator, then 𝐬𝐽 generator, 𝐬𝐽 calculator, actually device 𝐬𝐽 calculator, then analysis, then phonon, we have to select phonon transmission spectrum. Phonon transmission spectrum. For phonon transmission spectrum, first calculate dynamical matrix, then calculate phonon transmission spectrum. That's why it is a very time consuming calculations. So for our case, we have already simulated this phonon transmission input. So suppose phonon trans input is saved for phonon transmission spectrum, and after simulated, this is the output for phonon transmission spectrum. Actually, this is the transmission spectrum due to phonons. And now we will calculate the thermoelectric properties for due to phonons. And for ZT calculation, ZT means total thermoelectric figure of merit. We have to select for electronic transmission as well as phononic transmissions. So we will. So for this is the actually transmission for phonons, and this is the transmission for electrons. We have to select both for calculating total thermoelectric figure of merit. This is the actually total thermoelectric figure of merit. And this is the total thermal conductance due to electrons, due to phonons, and total thermal conductance. And Seebeck coefficient and other properties will not change because these are all due to electron. Actually, depends on the electronic part actually. And for the quantitative analysis, like suppose if you want to calculate percentage wise for acoustical and phonon contribution, we have to integrate the transmission equations, which is given in my recently published works, ACS applied energy, which is published in ACS applied energy materials. So thank you.
Deepak ji, so we are now ready to take few questions.
Yes, sir. So this session is open for the Q&A. So if anyone has any query, they can let us know.
Yes. Energy optimization process means when you are doing the optimization, that means we are actually optimizing the position, the coordinates of the atoms in terms of energy. So by varying the positions, there are several methods for that. We have used BFGS method here, and then energy is basically minimizing. And for energy minimizing, actually we have considered a particular K points, and we have considered some energy cutoff. For these two, actually, we have first set up a standard through our intuitions. We have considered a geometry, and QuantumATK 𝐬𝐤𝐸 gives you some default value. With the default value, start with the default value, and then it would be better first. What we follow is that first energy cutoff value we change, keeping the other things constant, that is K points and other things constant, default value. And then we note down at which particular energy cutoff our energy, total energy of the system changes in the milli electron volt range. Means after 3 decimal place it changes. That means up to milli electron volt it is constant. And then with that particular energy cutoff, we change the K points one by one and follow the same process. Where the energy changes is less, that means less than milli electron volt, that particular K points we choose. So now after energy cutoff and K point convergence, we get two values, one for energy cutoff, another for K points. Set these two and then do the final optimization, geometry optimization with these two values. Then you will get a geometry, optimized geometry, which is the minimum energy configuration of that structure. Okay, but it is not quite sure whether that particular structure is globally minima or not. For that, you have to do the phonon calculations and have to see whether any acoustic modes have negative frequency or not. If a particular mode has negative frequency, then for which particular vibrations is responsible for that particular modes, and then change the coordinate of that particular atoms along that particular directions where it vibrates. That means you distort the atoms in that particular directions, and then you redo the optimization process. And in this particular process, you may need to refine your criterias. Refine your criterias in the sense that you have to increase more energy cutoff, maybe more K point grid, the electronic convergence criteria maybe a little bit higher, and so on and so forth. So whatever, you have to play with that. It's not a very one just command calculations, but you have to play with it. Okay, QuantumATK is open source software? No, QuantumATK is most probably not open source software. Deepakji can answer better than me.
Any more questions, anyone? I think there is one more question in the chat box.
Does this thermoelectric analysis can be done for porous materials? Yes, our material, Priyadashini, this is our material is a porous material. You see, this graphite has hollow, and for battery material, actually we choose the structure in such a way that it has some void space, so that it can accommodate more number of ions. So porous material, but it's definitely has some symmetry. That means it has some particular structure, means crystal structure. If anything else you are using or you want to mean, please clarify. How to reconnect the electrode after okay, that procedure, Ankur, we have already demonstrated how to reconnect the electrode after optimization of central region. Okay. Hey, what? How to reconnect? How to? That means your question is how to make the device, most probably, right, Ankur? Ankur? Yes, that procedure we have shown. So if you want, we can demonstrate once more. But before that, I just want to Devanshu's question. I just want to tell. Yes, Devanshu, cohesive energy and formation energy both can be calculated using QuantumATK. For that, you have to calculate the energies of the P-Stein system with the single atoms. Single atoms, single different types of atoms involved in that one, and the absorbed system and the host material. Okay, and then there is formulas. You have to just put these values in the equations given in any of this paper. Okay, so there are so many examples of calculating cohesive energy and formation energy. One thing is that a little bit tricky is the formation energy, where you need chemical potential. So which chemical potential you will use for that? Okay, so that chemical potential, here we have used potassium and we have used carbon. That means carbon chemical potential, we have taken what is the chemical potential of carbon in graphite system, that is mostly available, and what is the chemical potential of bulk sodium. So that too we have used. Hey, so this device we are showing once more. Device, how to make the device?
So I am doing the process again quickly. So for device construction, you need to have the first optimized unit cell. From the optimized unit cell, you have to repeat it 3 times in the lateral direction. So now in my system, I am repeating in C direction 3 times. So here you can see the unit cell has been repeated 3 times. Now after repeating it, you have to go below the device. There is an option below a device from bulk. Choose that option and you will get the electrode length, electrode extension length, minimal electrode length. You will get these parameters. Now you can click OK. Your device is ready. So by this process, you can construct a device from a unit cell. Thank you.
Regarding this device, please ask.
So anybody has any other questions regarding the optimization convergence criteria or device?
একটা কোশ্চেন আছে, হাউ টু রিকনেক্ট ইলেকট্রোড আফটার অপটিমাইজেশন অফ সেন্টার
ওটা দেখে দিলাম।
वो एक property का है इसमें quantum capacitance.
Hi, any more questions, anyone?
Vaishnav Vishnu. Yes, quantum capacitance we have calculated, but in some other papers, and we are going to communicate one for that. Quantum capacitance calculations, you have to integrate this density of states. Standard formula is there. It's simply you have to integrate. Nirmal, can you please come here for this quantum capacitance? So you have standard formula for that, and you have to integrate. It's a very easy and thing, but it is not included in this talk. So in this, I will be happy to receive questions regarding this talk only. Otherwise, it will be very scattered, and people who are waiting for or listening this talk, they will be deprived a little bit. Otherwise, I can discuss this quantum capacitance. Yes, we have just published one PCC paper. If you get about reference to
Sir, I have already sent a tutorial regarding the quantum capacitance simulation by the QuantumATK in the chat box.
and just 1 minute you have a
মেল করতে পাঠিয়েছি আমি ডাইরেক্ট সার্চ করি স্যার আপনার গুগলে চলে গেছে
rules করে আছে এটা না কোনটা ছিল এটা না এটা you can see this link. It is already, I have already discussed in this link. Everything has been given, and it is using QuantumATK. Using QuantumATK, we have just published this paper, and is discussed how to calculate. If the device is heterogeneous, means there is a barrier layer of different materials, and how to optimize and make it has. Yes. So Ankur, yes, you can make heterojunctions of this, but for that actually heterojunctions we have not shown here. It's another. Say process is same. Only thing is that most probably what you have faced is that you have make a structure like this. You have taken another structure like this. These two are heterostructure, and when you are making interface of this, it may becomes like this, one above the other. But you are trying to take like this in the same plane, right? That might be the case you want, but what you are getting is like this. So in that case, what I propose is that, so you get the initial of this one, you get the initial of this one, then just make a translation of this particular structure in these directions, so along z directions, and then translate it along these directions, and then try to find the positions in between these two, so that this interaction region and the bond length in these heterojunctions are matching as you expected, and then do a quick optimizations with loose criteria, then you most probably will get it. But mind that you will not get the symmetry definitely, because it is a heterostructure. So symmetry is another problem. If it has some other symmetry, then that may be written, but otherwise both the symmetry for structure 1 and structure 2, that will be loose definitely in the heterostructure.
So I see there are no questions left. If there are any, just let us know. Okay, so I think I should conclude this session. So as we come to the closure of this insightful session, I would like to extend my gratitude to both our esteemed speakers for their valuable contribution. First and foremost, a sincere thank to you, Dr. Utpal Sarkar, for sharing his profound research insights of novel carbon networks using Synopsys QuantumATK. Your presentation has provided a deep understanding of how atomistic simulations are transforming the landscape of novel carbon and materials research. Apart from this, I would also like to extend my gratitude to Mr. Nirmal Barman and Ms. Sadhana Barman for the excellent live demonstration. Your practical walkthrough of the QuantumATK platform greatly enhanced our understanding of the discussed concepts and provided a valuable hands-on perspective. Together, your combined expertise has made this 10th session of the Faculty Interaction webinar series both enriching and inspiring. A special thanks to all the faculty members, researchers, and participants who joined us today. Your engagement and active participations are what makes this webinar series meaningful and impactful. We look forward to welcoming you all to our next session of the Faculty Interaction webinar series. Until then, stay safe, stay curious, and keep exploring. Thank you all once again, and have a great day. Thank you once again, sir.
Thank you.